Welcome back to Bite-Sized Breakthroughs, where we explore the cutting edge of artificial intelligence. Today, we're diving into a fascinating paper that tackles the persistent problem of slow learning in deep reinforcement learning. Joining me is Dr. Paige Turner, a leading researcher in this field, and Professor Wad Spectrum, a renowned AI expert. Paige, can you give us a quick introduction to this research and its significance?
Thanks, Alex. This paper, titled RL2, Fast Reinforcement Learning via Slow Reinforcement Learning, tackles a critical issue in the world of deep reinforcement learning. Imagine teaching a robot how to walk. It takes many tries before it masters the task. In contrast, humans and animals learn much faster, often after just a few attempts. This paper delves into why that gap exists and proposes a novel approach to bridging it.
That's a great starting point. Professor Spectrum, could you shed some light on the historical context of this research? Why is learning speed such a critical issue in Deep RL?
Alex, you're right to emphasize the importance of learning speed. Deep RL has made remarkable strides in areas like playing Atari games and controlling robots, but it often suffers from high sample complexity. For instance, state-of-the-art Atari agents might require tens of thousands of episodes of experience to master a single game, equivalent to playing for 40 days without a break. This stark contrast with human and animal learning highlights the need for more efficient methods. The challenge lies in the lack of good priors, a way to incorporate past knowledge in existing deep RL algorithms. They essentially learn from scratch, which makes the process slow and inefficient.
So, Paige, what's the innovative solution proposed in this paper? How does RL2 differ from traditional approaches to incorporating prior knowledge?
Instead of hand-designing algorithms with specific prior knowledge, RL2 adopts a meta-learning approach. It treats the process of learning itself as an objective, which can be optimized using standard RL algorithms. This means RL2 learns a fast RL algorithm by encoding it within a recurrent neural network, RNN. This RNN, which we call RL2, receives observations, actions, rewards, and termination flags as input. It maintains its internal state across episodes, effectively storing and updating its knowledge as it interacts with the environment.
That's fascinating, Paige. But how does this RNN actually learn the RL algorithm? Can you elaborate on the methodology?
Sure. Imagine the RNN as a student learning how to solve problems. Instead of being directly taught by a teacher, the student learns through a series of self-guided practice problems. In RL2, the RNN's weights are learned using a general-purpose, slow RL algorithm called Trust Region Policy Optimization, TRPO. The goal is to maximize the expected total discounted reward accumulated during a trial, which consists of multiple episodes with a fixed MDP. Each trial represents a new problem for the RNN to learn from. As the RNN interacts with different MDPs, it gradually learns to adapt its strategy based on the information gathered from previous episodes.
This is starting to get complex, Paige. For our listeners, can you break down the core elements of the method in a more straightforward way?
Certainly. RL2 utilizes a recurrent neural network, a type of artificial neural network that can process sequences of data to represent the RL algorithm. This RNN is trained using a slow, general-purpose RL algorithm, similar to teaching a student through practice problems. The RNN maintains its internal state across episodes, accumulating knowledge and adapting its strategy based on past experiences. It effectively learns a fast RL algorithm that can handle various scenarios it encounters.
Professor Spectrum, how does this compare to traditional approaches of incorporating prior knowledge in RL? Are there any similarities or notable differences?
Traditional methods often rely on Bayesian reinforcement learning or hand-designed algorithms that incorporate specific prior knowledge. Bayesian RL, while theoretically sound, often becomes computationally intractable in complex scenarios. Hand-designed algorithms, on the other hand, might be limited in their applicability or might become computationally challenging in high-dimensional settings. RL2 offers a refreshing alternative. It avoids the limitations of these methods by learning the RL algorithm implicitly through a recurrent neural network. This makes it adaptable and potentially more scalable to complex scenarios.
That's a great explanation, Prof. Spectrum. Paige, let's delve into the experiments. Can you tell us about the tasks used to evaluate RL2?
The authors evaluated RL2 on a range of tasks, starting with classic problems like multi-armed bandits and tabular MDPs. These tasks have been extensively studied, and there are algorithms with theoretical optimality guarantees. The goal was to see if RL2 could achieve comparable performance. They also evaluated RL2 on a more complex, high-dimensional task called visual navigation, where an agent must learn to navigate a maze to find a target using only visual information.
So, what were the results? Did RL2 live up to expectations?
The results were impressive. For multi-armed bandits, RL2 achieved performance close to that of theoretically optimal algorithms like Gittin's index and UCB1. This was particularly impressive for settings with a limited number of episodes, showcasing RL2's ability to efficiently balance exploration and exploitation. In tabular MDPs, RL2 outperformed existing Bayesian RL methods for a smaller number of episodes, suggesting its ability to learn quickly and adapt to new MDPs. The visual navigation task was more complex. Here, RL2 demonstrated successful learning and generalization. The agent showed improvement in trajectory length and success rate between the first two episodes, indicating its ability to learn and utilize information from past experiences. It also exhibited reasonable extrapolation behavior to larger mazes and longer episodes, further demonstrating its potential.
That's really encouraging, Paige. But as with any new approach, there are likely limitations. Proffer Spectrum, what are some potential drawbacks or areas where RL2 could be improved?
Alex, you raise a valid point. One major limitation is the performance of the outer loop RL algorithm, which is responsible for learning the RNN's weights. It serves as a bottleneck, affecting the overall effectiveness of RL2. Exploring more sophisticated RL algorithms for this outer loop is critical to further improving performance. Additionally, the current architecture of the RNN might not be optimal for tasks with extremely long horizons. This suggests that future research should focus on developing architectures that are better suited for handling long-term dependencies and complex temporal relationships. Finally, RL2's evaluation is primarily focused on a limited set of classical tasks. Further research is needed to assess its effectiveness and scalability on more complex and realistic real-world problems.
Excellent points, Prof. Spectrum. Paige, what are some of the exciting directions for future research building upon this work?
There are several exciting directions for future research. One key area is to explore more advanced reinforcement learning algorithms for the outer loop, focusing on those with better sample efficiency and robustness. We could also investigate specialized architectures for the RNN that leverage the episodic structure of the problems, potentially leading to improved performance and generalization capabilities. Additionally, extending RL2 to handle more complex and realistic real-world tasks, including those with continuous state and action spaces, is crucial for practical applications. Understanding the relationship between the choice of prior distribution over MDPs and the performance of RL2 is also valuable, providing insights into how to effectively incorporate domain knowledge into the learning process. Finally, investigating the use of RL2 for meta-learning in other domains, such as supervised learning or natural language processing, could open up new and impactful applications.
Those are great directions for future research. Proffer Spectrum, what are the potential broader implications of this research and its potential applications?
Alex, this research has the potential to transform the field of reinforcement learning. By enabling faster and more adaptable agents, it could revolutionize areas like robotics, gaming, and healthcare. In robotics, RL2 could lead to robots that learn new tasks quickly, adapt to changing environments, and perform complex actions with limited data. In gaming, it could create more intelligent and adaptable game characters and agents. In healthcare, it could develop personalized treatment plans for patients by learning from individual medical data and adapting treatments based on their responses. RL2's success in scaling to high-dimensional tasks suggests that it has the potential to address real-world challenges in these areas and beyond.
Thank you both for this fascinating discussion. It's clear that RL2 represents a significant advancement in the field of reinforcement learning. It opens up a new paradigm for designing more efficient and adaptable agents, with exciting implications for a wide range of applications. Paige, any final thoughts?
Absolutely. This research demonstrates the potential of meta learning in reinforcement learning. By learning the RL algorithm itself, RL2 bridges the gap between human and animal learning and the current limitations of deep RL algorithms. This innovative approach has the potential to create a new generation of AI systems that are more adaptable, more data efficient, and more capable of learning and performing in complex real world environments.
Thank you, Paige and Prof. Spectrum. This has been a truly insightful discussion. We'll continue to follow the development of this research and its potential impact on the future of AI. Stay tuned for more bite-sized breakthroughs.